Okay, good. Wow, that was quick. So, we have 60 minutes. I have 40-something slides, so this is going to be very difficult. I will not do any code demos except showing you code because we have a lot of material to cover, a lot of scenarios to cover. This is a deep dive. So I'm making some broad assumptions here. I'm making some broad assumptions that you know just generally what Service Bus is about. And we're going to be mostly focusing on scenarios and capabilities around messaging. So I'm going to enumerate a lot of features to you. And I'm going to explain in the context how you can use those features. So that's how you should imagine this session. So learn about messaging patterns, Service Bus, connectivity, messaging, service management, integration, things that I talked about yesterday. We're not going to cover the relay much in this session. We're not going to go and drill deep into that. We're going to be mostly focusing on the messaging area and about queuing, pub/sub, and how to build applications with those capabilities, both for intra application messaging and going across. Then, do I still have AppFabric? Oh, so you make a point here. Wonderful. Look at that. I still have AppFabric on here. So, you just saw the change live. I deleted the AppFabric brand. That's what we did a few months ago, 2 months ago. We got rid of the AppFabric name because we're good about optimizing. So now the brand name for Service Bus is no longer 5 words, but 4 words. 20% better. I have hope that eventually we're going to get to the point where we're going to name things with simpler names than 4 or 5 or 6 names. But cutting out AppFabric is already a good thing. So the platform is called Windows Azure. Service Bus is a feature of it, and so that's why we dropped the name AppFabric. So let's talk about hybrid applications and how we're thinking about those. Service Bus specifically is for intra-app messaging and for cross-application messaging. And a hybrid application is one that interconnects all those things, where you have one solution composed of multiple different apps. And more and more we're seeing solutions like this. The rise of consumer devices like the iPad, Exhibit A, has brought us native applications on those devices, has brought us applications that are applications in their own. If you think about HTML5 and putting a lot of JavaScript in there, that's an app. That's no longer just some markup that you send to the client. And so we're having composite applications that run across multiple tiers, and you need to have communication between them. And so we're going to go and talk about multiple of those application patterns towards the end. I'm also going to talk very briefly about SignalR. SignalR is a framework that's built by ASP.NET, or by some people inside of ASP.NET. And they're going to bring out a new version shortly. They're testing that last version. That will also be enhanced with Service Bus, and we're going to talk about how that works and for what scenarios that is. Some general advice when we talk about hybrid applications, when we talk about applications that span the cloud, on-premises, and devices. The first advice is, when you think about cloud apps, when you think about adding cloud to the mix, if you have so far only built applications that are local, and if you now want to go and mix applications that are local with cloud scale and with devices, the first thing to notice is that latency will now matter. One of the things that we're seeing fairly consistently with customers who are taking this step and building cloud applications is that latency suddenly starts to impact the architectures. You will not get LAN throughput on TCP. So there's a general rule, the laws of physics work against you. The reason why I have the Einstein formula here is because it limits the speed of light. Right? This is why the speed of light, speed of light is a constant. If you do the math, then if you make this any faster, then things are just not going to work out. So latency, when you go across from your site to a data center and back, the signals cannot travel faster than the speed of light. That's simple. 10 milliseconds. Well, 20 milliseconds, and they need to go through switches, and all that time actually adds up. So we see see impact. You will see impact on throughput. The throughput of TCP, just to remind you, all know this, I'm just reminding you of this, is the throughput ceiling is defined as the size of the receive window divided by the latency in seconds. So if you have a receive window of 64K and you have latency of 100 milliseconds, you get 640 kilobytes of throughput on that one socket. 6.4 megabits. That's it. You can't get more. So these are realities that are sitting outside the network, and you have to deal with them, because the worse the internet connection gets, the more packet loss you have, the more you're constrained. That's just how a TCP works. So that's as some piece of general advice. So think about latency, and we're going to talk about generally, when you talk about hybrid applications, when you talk about those kinds of apps, latency is there for you. So think of that. Don't make super chatty calls, bunch data together, etc. Just as a word of advice before we go into the details here. All right, so general advice out of the way. Let's talk with service bus. So when we have a queue, and that's something that I mentioned already in yesterday's session, but for the folks who weren't here for that for the yesterday's session, when you have a queue, you get some really nice additional features kind of for free for your app. The first one is load leveling. Load leveling, you have the sender sends into the queue, the receiver receives on its own pace. So the receiver is actually completely decoupled from all and any stress that the sender puts on them. The sender can send 500 messages a second. If the receiver can only process 10 messages a second, well, then the log in the queue is going to be longer. And eventually, you're going to exceed the size of the queue. In Service Bus, the sizes of the queues are limited to 5 gigabytes if you choose to. The default is 1 gigabyte. But the receiver is never going to be stressed out. So that gives you a very nice load leveling. Typically, where you get this is when you have sites, websites, and we're going to talk about websites in the context of correlation, that get very spiky traffic. So when you get very spiky traffic, then the load leveling of the decoupling, basically inverting the direction here so that the receiver pulls the data, is helping you dealing with that load. So having a queue in the middle is very useful. It's also useful if the receivers that are sitting at the back are not always online. So they might be offline because the network connection maybe is bad. So if you have an application that needs to talk to devices, and the devices sit on a bad network, like this here, then, and because it's overloaded, right? This is all not meant for so many people in one place. The worst thing that can happen is a sports stadium where you just can't get the density in the cellular network to actually make it work. So if devices are offline, if they need to work under those circumstances, then you can make little mailboxes for them in the form of queues, or more appropriately in the form of subscriptions on a topic, and then they come by and just get the messages as they come online. You can also do batching with it very nicely. You just use a queue as a batch. You send data into the queue over the course of an hour or a day, and then a process spins up, drains the queue, does the processing, and then goes to sleep again. So you can go and do basically hour by hour or day by day processing by just putting all the work into the queue and then getting it out later. Load balancing is also a wonderful pattern that you get out of the broker. Comes with, effectively, it's another effect of the load leveling of the reversal of direction. You have a receiver, you have multiple concurrent receivers which sit on the queue, and each of the receivers is a loop. And a loop, in the simplest case, sits on a thread and does receive, work, receive, work, receive, work. You put multiple threads concurrently, well, then you can actually do 3 times as much work until the machine is loaded, and then you add another machine. until that is loaded, until that can't do any more. But you can hook them all up on the same queue, and with that you get very nice load balancing between them, and nobody gets stressed out. So that's a wonderful advantage, and it's very different from HTTP, where you just have enough capacity, you hope, and then the load balancer goes and just sprays that load across all those machines without any respect for load, because HTTP load balancing is hardly load balancing, it's just connection balancing. Because it doesn't take the load into respect, and queuing does that. By the way, not to mention my my personal wares all that much, but I have there's a course on the Plural site where I explain effectively also the process models, and to give you an insight into this, when you think about how the process models work in the operating system in various stages, down from the OS scheduler up to scheduling models as you find in Serverless, as you find on effectively all the UI stacks, they're all going with a pool and a queue. Everything is scheduled through a queue. If you're familiar with Silverlight, for instance, all work in Silverlight needs to be async. Well, it doesn't need to be async because it's scheduled through a queue. There's one thread that executes. And it's all done through a single queue. It's using a queuing capabilities, and you have effectively scheduling multiple logical threads of execution all through that single queue. Windows works like that. Since Windows 1.0, there's a message loop, and that's driving the UI of Windows. Fan in. So what we have here is load balancing basically multiple concurrent consumers on a queue. Fan in is multiple concurrent senders into a queue, where the queue now acts as a concentrator. So you have multiple senders. You can get the highest throughput on Service Bus by having multiple senders, make multiple send threads. The reason for that is that if you think about the limitations that I just talked about, right, on 100 milliseconds latency, 640 kilobytes throughput limit theoretical for a TCP socket. If you need more throughput, and we can actually handle more throughput, we can do up to 10 logically very easily. We can actually do up to about 30, 40 megabits in the peak for a queue. And then you can actually go across multiple queues and shard this up. I'm going to mention that later as well. Then you can't even pump as much data through a TCP socket, discounting overhead and message packet loss, etc. You can't get so much through to a socket as we can actually handle at the back end. So one of the things you should do, if you can, is make multiple connections, multiple concurrent senders to send data into Service Bus, because that will help you. So the concentrator model, the concentrator pattern, runs it all through the queue, so you have multiple senders from multiple places, and you get a consolidated stream out of a single queue. There's a multi-stage aggregation model that we, for instance, use inside of our own infrastructure for billing. What's interesting, especially around eventing, when you think about eventing at scale, you can easily see that in your own systems on Diagnostics, is do you have more data that you can handle? So just think about Diagnostics and event management. Let's say you want to consolidate all the alerts you're getting out of a system. Let's say you run a system that consists of 100 nodes. And now something happens on the network. Or you have a significant event that happens somewhere in your hardware fabric. And now all those machines start spewing out errors. That might be so much load that it now actually makes the problem worse. So what you want to do is you want to do local roll-up. Effectively, just do the most important information, roll that up locally as close to the data source as you can, and then only send that further. Same goes for with billing data. So with billing data, I can make that even a little more transparent. Inside of Windows Azure, inside of Service Bus, we're charging you for things. Right? So whenever you send a message, the message counts towards the total message count. If you have a connection in the relay, an endpoint in the relay, we're counting hours. So we're doing all that billing. Our Front end has 32 nodes, our back end has 16 nodes, so that's a sizable fabric. And we have all these meters running. We have 30,000, 40,000 namespaces on one of those fabrics. So there's quite a bit of traffic on there. If we took every billable event, which is every message, and sent a message for it, we'd be swamping ourselves. So what we do is we have internal queues on the machines, which that data runs into. Then we roll the data up in 5-minute intervals. Then we go to another queue off the machine, roll that up further, and then every hour we actually emit per namespace an event into the billing system. So you have a multi-stage fan-in, roll-up. Then there's fan-out. For fan-out, you use topics. For fan-in, you can also use topics, right? But the queue and the topic are looking exactly the same. With a topic, you can do message distribution. So you have multiple destinations to which you want to send data. And the simplest case for distribution, and why you would almost always want to have a topic instead of a queue, is because you can put tabs. And a tab means that you can have always, on an existing topic that just acts like a queue, you can always add another subscription and just get at the message stream. And if it's only for diagnostics purposes. So in the sample here, and that's a sample you can actually get inside this, just in the SDK. Here I'm setting up these topics, or this one topic, and I'm creating, if it's not existing, I'm creating that topic, and then I'm creating a number of subscriptions, and I have 2 subscriptions here that are not for the mainline processing, but they're just there to basically get a handle on the messages. So there's an audit subscription, and that logs all the messages that come in. So you can go and effectively put a listener on this and go and just write them off into storage. This is all the raw data that came in, without disturbing the flow that's going into the mainline system. And then there's a blind tap here. It's also an explicit subscription with a false filter. And the false filter means no messages are selected for that thing, but you can go in at runtime and you can enable this. And you can go and set a rule for what messages you want to get. So if you are looking for particular messages that are coming in and you want to filter them out for diagnostics, you can go and basically just go into your blind tap and get them all out. So instead of using a queue, just use one where you have a default subscription with a true filter, and then you can add an auto subscription, you can add an additional tab, you can add whatever you want, and every time you get a message. Now, that comes at a cost. Every time you have a filter and the filter gets selected, you're producing a copy of the message. The throughput of a topic varies, right? I'm going to give you a number, but don't hold me. So we currently we don't give you any SLAs on throughput. So I'm just going to give you a number. A topic can do about 2,000 messages per second as entity throughput. Sometimes it's 1,000, sometimes it's 2,000. So 2,000 is an average good day. So this is entity throughput. If you have 2,000 subscriptions, your flow rate is 1 message per second. Because you send 1 message in, you get 2,000 messages out. So your flow rate through everything is 1 message per second, 2,000 message copies which are flowing in parallel. So that's how you do the math on the throughput of a topic. Every message copy counts towards that total entity throughput number. So message distribution is effectively just fan out, and you can do fan out for all kinds of reasons. An interesting one is constraint message distribution based on filtering, based on partitioning. So the filters allow you to add rules, and each match rule yields a copy of the message, and you can use these SQL 92 expressions. So I'm setting this up here as well. At the subscription, and if the ship country is US, then the messages should match this. If the ship country is DE, then the messages should match this filter. These expressions here, this here is a reference to a message property. So messages are flowing, and they have a body, and then they have a set of key value pairs, and this is an expression that's in these key value pairs. That's a property, and you can run these expressions. And we support SQL syntax, so you can do ands and ors, and you can use parentheses around sub-expressions, and we support full arithmetic, including meanwhile also modulo. Modulo being important if you want to run some simple partitioning math on it. Partitioning is using filters, very simple, and you just make some mutually exclusive ranges. So you have some partitioning logic that you're using, and using mutually exclusive ranges. Even though not directly related to service bus, let me just give you a simple example for how you can do partitioning. Partitioning, I distinguish in partitioning between partitions and shards. Shards is a physical thing. Partition is a logical thing. So you create in a system more partitions than you ever will have shards. Shards is, think of shard as a database. And you have lots of data, and you want to put this into 4 distinct databases, 4 distinct partitions, 4 distinct partitions in the table store. And you make more partitions than you would ever need. So if you want to redistribute load across these shards, you can do that by simply shifting the assignments. So you make 100,000 partitions. If you want to assign a customer record to a partition, you take the customer's name or customer ID. Customer ID is something that's better because it doesn't change. And then you compute that to a number between 1 and 100,000. And that's very simple. You run a hash over it, or if it's a number, and if it's a number greater than 100,000, you just divide it, or do a mod, do something. And that yields a partition number. And each shard owns a range of partition numbers, and that's how you do the partitioning. That's how you do the mapping between shards and partitions. If you need to have more shards, you basically just redistribute the load of the partitions to those shards. And the way how you drive traffic towards those shards is using that kind of logic. You just publish the message into the topic, and the topic contains the logic for what shard has which range, because that's completely transparent to the sender. The sender just sends messages, and you can go and reshape the system at the back of it by just changing the subscriptions, adding subscriptions, and also changing the rule on the fly if you need to. So the rule conditions allow you to do that kind of partitioning, to do distribution. Now distribution can also be, so I'm just giving an example based on ranges. Partitioning is also something that can be regional, as we have in our example here, the ship destination country. But you can also have, let's say you are getting orders, right? Purchase orders or delivery orders, so that someone has bought something, now you need to ship it, and you have 3 delivery centers around the country. Well, the way you can route that data is by just having each delivery center go sit on a subscription. You send the message there. The partitioning is actually done here. It's checking by region, whatever, and that gets assigned to that particular location. So these are the basic foundational patterns. Partitioning, distribution, load leveling, load distribution are all basic patterns. Now let's talk about some composite patterns. The first one is update read separation. That's a very foundational, very old principle. It's basically batching, if you will. There's a crowd of fairly young architects going around and making a set of patterns, CQRS, command query separation, responsibility segregation, and event sourcing, and a particular style of analysis and design, DDD. They're making that popular. They're liking it. And this pattern is something that's foundational for that effort, where you're effectively in a system separating the read and the write paths. And that's something that's not enormously new. I'll give you an example. Amazon. Think of Amazon, the catalog. The catalog of Amazon is not edited and sitting in a single database. Right? When you look at the catalog, you're looking at a copy of the database. There's a master database. There's multiple master databases, multiple departments. Each department manages their catalog. They're putting that into separate systems. Each department has a separate system, and that data gets broadly distributed, gets broadly replicated and cached in the system. So there's a master copy, probably multiple master copies, and that then gets replicated. Now, you can go and use a topic very nicely to create these read copies. So you have a master system. You have the client, and the client sends data straight to a topic. Or probably there's a master system that sits up here that goes and verifies the input, sees whether it's plausible, and then writes that input into, it may have a verification database, and then writes that data into a topic. And then you can have multiple projections, read data projections, that each have a subscriber into that event stream, where now the database that you read from kind of automatically builds itself as a projection out of the message flow that you have here. Ultimately, this is like a transaction log. The way a database works, again, to remind you, is when you do a transaction in SQL, you create a transaction record. You say, I'm going to update the following record, or the following table. I'm going to add the following fields to the following row. So you're effectively writing a delta into the system. So here's the same. You have an event. You have something that you have determined in your system that you're going to do that. And now you're writing that into a transaction log. And the transaction log here really is a topic. And you can materialize this in the reader here into any structure that you like. So you can have a highly denormalized store for one purpose, a highly denormalized store for another purpose, and the clients can go and read it. So let's say you have your catalog. You have your catalog that's specially built for mobile devices. You have a catalog that's specially built for the web. You have an index for browsing the catalog. You have details, and you can go and effectively create all these different projections out of a single event stream using a topic. Update notification is another thing. If you have a lot of caches in your system, you need to keep those caches coherent. One way to do this is to use expirations and to effectively invalidate the data in your cache or into your intermediary systems when some time expires, or you proactively, whenever something changes, you tell your caches. So that's what the update notification is all about. When you go and the sender here writes a record into the database, and as it writes a record into the database, it also writes that update into the topic. And anybody who has interest in that particular record will go and read it. For a number of systems, that's actually very interactive. So we have a capability inside of our system that we're currently building that I mentioned yesterday, I think, for push notifications. And so that's something that we're building out. We're going to have this later towards the end of the year. We're going to support Windows 8 with push notifications into the shell. And part of that system kind of needs to have a cache for jobs. So these are jobs that are executed on a regular schedule. The system will never touch its database, except when it boots up. So whenever a node boots up, it sucks the database in that's full of those jobs. It will figure out what it owns. And then whenever there's a change being pushed into the system, that change is not read from the database, but it's actually read from that topic. So that's how that's how the workers learn about additions into the system. They're all communicated all through the topic, and only when the systems boot up, they actually read the database. Makes it much more efficient, and actually makes it quite a bit more agile inside the system, because it can quicker react to changes. So we're using that as an information distribution backplane inside of our system. Diagnostic statistics I already mentioned. That's a model where you have a lot of fan-in and where you have fan-out, and you can go and use the topic infrastructure. You can specifically use rules. It's quite warm in here, isn't it? It's not just me. I wish I could take this off, but you're not going to like that. Sorry that it's so warm in here. I apologize on behalf of Microsoft Corporation. When you work at Microsoft, that's one thing you learn. Just apologize. It's okay. It grows on you. You're fine. So what you can do here is you can make a subscription. So you have an event stream, and you're just pumping all the events that you get. You're just pumping that into the topic infrastructure. But you're not interested in all events. Typically, you will only be interested in events that are really severe, like things really going down the drain. But you don't want to miss those. So you have events of category 1, oh my God, something really terrible happened. So what you do is you're going to put a filter in here that says severity, so a filter condition, severity equals 1. And now you can have an action, and the action modifies a property. So for those, you will set the TTL. You have an action that's called set sys.ttl, or sorry, sys.time-to-live equals some long number. For severity 3, which is all the usual chatter, you will set a rule that says severity 3, sys.time-to-live equals 5 minutes, 1 minute. So that whenever you walk up to that topic, you will get the last minute of recorded data, because that's likely what you're going to be interested in, and nothing else. So you can actually triage a diagnostic stream by severity for diagnostics purposes. So that's something that's very important. One of the things that we've learned in the platform is never neglect this part of the system. Windows, so the service bus is like an iceberg. You see the shiny part that's above the water. That's about 15% of what we have built. Everything else is under the water. It's all support systems, engineering systems, diagnostics, operational management, and all those things. And so things like this are very important, are part of it. Building a large commercial web service is a huge, huge undertaking. And the features that we give you are only a fraction of it. So I'm giving you a little bit of insight into the kind of infrastructure we need at the back. And so we're doing things like this. Correlation is another of these composite patterns, where you, and this is where the website gets in, where you have now a caller, and the caller sends data into a queue that's owned by a receiver and says, hey, if you have a reply, go send me a reply into the following queue, this queue, and please use the following ID that I'm passing you, this correlation ID, and please copy that into the message. The correlation ID is being set up here, and then you basically just copy that correlation ID into the reply message so that the sender can re-identify that message. That gives you a request-reply path. And from there, we can actually expand, and we can go and make this a case for, let's say, ASP.NET. You have an ASP.NET request loop. Right? You come in with a request, and now you want to have something happening at the back end reliably. Someone just gave you their credit card and said, please execute this order. You can do it in the optimistic fashion and just try, and have all kinds of failure situations happening, or you can put it into a queue. Once you have it safely on the queue, well, now you can actually, now we have enough reliability in the system to deal with that, even if, let's say, this connection tears up. So the client just comes in and says, post with a request, and now the connection goes away. What happens? That's the big undefined case in web commerce. So as soon as you need to have reliability at the back end, this is actually not a bad idea. So you go, and from a sender, you go into the send queue. Because you specify the queue name, the receiver now knows what reply to go to, and can can return the message. What that also does is it nicely manages, and this is why it's a composite pattern, manages the load. You have super spiky traffic on the front end on the web. Now you're submitting all these requests. You can't stress out the back end, because the back end has a nominal capacity, and it will pull with that nominal capacity. It has a receive loop, get one message, do the work, get one message, do the work, get one message, do the work. Whether there's 2,000 senders concurrent on the front, that thing doesn't care. You can make it care by observing the queue length. What comes out of that is more receivers. So observing the queue length, you can first make more threads, and then if you really are running out of capacity, you can make more workers. One of the things that's only semi-ideal in the way we're probably talking about Windows Azure is you should actually make your workers a little more dense. A good idea is to take multiple kinds of works and just put them into a worker and then turn that functionality on or off as you need capacity. So if you have sometimes you need to have a lot of order processing. Sometimes you need to have a lot of other work that you do. You can all consolidate that into your worker role and then turn functionality on or off as you need it in the system instead of having to go deploy extra capacity. That's a smarter way to do this instead of always using a worker role. Think of that as a complete dedicated VM, just having more of that work sitting in there. And one way you can go and turn things on and off is, of course, use a message queue. Right? You can make your worker role listen for commands over a queue, and then you send it these control commands. So say, turn this functionality on, turn this functionality off. You can effectively go and create a control backplane using messaging. For correlation, we have three models. Message-based correlation, we have subscription correlation, where you correlate on topics, and session correlation. There's a video online where I go into that in a little more detail. Unfortunately, we only have an hour, so I'm going to skip the further details here. Sessions. Sessions are a fairly unique feature of Service Bus compared to other infrastructures, other messaging infrastructures. And what they give you is work set pinning. Work set pinning meaning you can send a set of messages that are related to each other. To do this, you go and you create the queue with require session equal true. Once you do this, you have sessions enabled. And what that does is you can now go and send messages into the system, and you can set the session ID of that message. You can set that to whatever you like. When we see messages coming in with the same session ID, we're going to assign them to the same session inside of the system. Effectively, what you get with that is a multiplexing model. Everything that is labeled with the same session ID goes into the same session, which is a logical construct for sending. On the receive side, it actually has a more profound effect. When you have a sessionful queue like this, or a sessionful subscription like this, and this is how you send, right? You just set the session ID, which is up to you, it's just a string. Then you no longer receive simply on a queue client or on a subscription client, but instead you accept a message session. The message session is a special kind of receiver, and you can call receive on it. What happens when you have a message session receiver, and you can either specify the session ID or you leave the session ID off. When you have one of those sessions, all messages labeled with that same session ID are pinned to your client, which means you start accepting the message session. Everything that's now labeled with the same session ID comes to you. Even if you have multiple concurrent threads, multiple concurrent machines, everything that comes with that session ID comes to this place. Which means if you need to address the fact that our messages, the message size is constrained, we will only allow 256 kilobytes of memory, 256 kilobytes per message. But if you send larger messages, what you do is you chop up the payload and you send it in the session, and then they all show up in the same place. They show up at the same receiver. you say, hey, 256 kilobyte, that's unacceptable. That's too small. My payloads are much bigger. I hear you. There's a hard reason for that while we're doing this, because we're running a cloud service, very, very many machines. We want to have very, very many connections. You ask us for a big high scale, and I only have so much memory. That's the reason. So I need to pick me with the leadership of our dev team and test team. We need to pick a number. And the number we picked is 256K. We might go up to 1 megabyte, but that's the ceiling. That's it. I'm not going to allow more. Because we can't. Because we need to make copies of the messages in the system. We need to juggle them. But the way out is to do these sessions. What we might do in the future, or what's likely we're going to do in the future, is we're going to put some nice scaffolding around this and make it pretty, so that we're going to create the illusion of creating larger messages, but ultimately underneath the mechanism is going to stay the same. We're going to use sessions for this. Now what might happen here is you're sending 4 gigabyte of data. And so you're chopping the data up and you're sending it using a session, always the same session ID, where the session ID might be a file name or a GUID. So the receiver gets the data. 2 gigabytes into the transfer, the receiver dies. Power goes out. The Windows Azure Fabric controller comes around, shoots a worker roll in the head. It does that from time to time. Right? The Fabric controller walks around and says, I have an update. You come here. So that happens to your worker roles, and that's something you need to expect. We're designing all of our system, by the way, for the case that someone can walk up to the rack. If nobody walks up to the racks, by the way, in Windows Azure, but if they would. But if anybody would walk into the rack and simply just brutally rip a machine out, nothing can happen to the system. In the early days, we actually did exactly those tests. Like we sent people into the labs before we had the Windows Azure data centers and had them actually pull the machines out, because nothing can happen to those things. So we need to be prepared for those cases. And how do you do that? We have session state. What an idea. So you can go and get a message out, and you can record where you are and write that back into the queue. You have a little bucket of state, one message large, that you can write data into. You can actually write that into that state bucket in the context of a transaction, where you're managing the transaction using a normal transaction scope, and you can go and get the message and set the state and complete the message. This is the peak lock pattern that we have, all in a single transaction. Transactions, we only allow transactions against the broker itself, not together with SQL Server, but just against us. But you make it one atomic operation. So that's how you do that. So you accept the message session, you receive, and then you can set the state, and then you would go and say message.complete in a single transaction, and with that you can effectively record the state of where you are. So let me give you a quick scenario for this. Let's say we'll build a game in our heads very quickly. We're going to build a game of roulette. So you have a table in a casino, right? In our virtual casino. Nobody's in the table. Nobody's in the casino. You show up and you say, hey, I want to bet some money. So you're going to put some money on the table on a number. The casino wakes up. Your session ID for that is a table number. So we have a queue, right? We have a receiver. The receiver is our generic roulette engine. So you show up with a brand new session. How do we know it's a brand new session? Because we look at the session state, we say get state, and find that the session state is null, which means there's no game going on. So we get our message. We create our little roulette table, and then we're very sinister because we're going to roll the dice and already make the number, and we're going to send ourselves a message 2 minutes into the future. I'm going to show you that feature in a moment. So we already know the game is going to be over in 2 minutes. Now other people can go show up at the same table, sending messages to the same table ID, and add them. Whenever that happens, our generic roulette handler, that can also be scaled across multiple machines, gets a message, right? Gets the session, gets the message, reads the state, puts that message onto the board, right? So puts that table onto the board and writes the state back. Gets the next message, writes it onto the board, puts the state back. At some point, the message shows up that completes the game. We look at the state of our game. We distribute the winnings and set the session state back to null. Table is empty. We can run that roulette game, hundreds of thousands of them, concurrently, because we can effectively scale this to hundreds of nodes, which are all just getting messages, and because they're all completely independent, because all that state just sits in that queue. There's no local state. What I just described to you, that roulette table is a state machine. Workflows are state machines. Turns out that feature is built for workflow. So the workflow engine underlying Office 365 in the next version is using Service Bus to actually store its state exactly that way. So if you need to have a distributed state engine, you can use that feature. Transactions. We have local transaction support, as I just said. So you can put the several operations together, and that creates batches on send. It creates effectively reliable DQ operations together with the session state on receive. There's no distributed transaction support. We don't have any support for DTC. The reason why we don't have support for DTC in the cloud is simply because DTC is causing locks to be set on our backend stores, and we can't afford anybody to be in the control of our backend locks who's not ourselves. Because that would cause locking and blocking, would reduce the scalability of the system. You will find no cloud infrastructure today which implements at scale DTC. Also, the two-phase commit protocols are not built for high latency, are not built for effectively low trust environments. So we can't support this. For an eventual server version of Service Bus, we're currently strongly considering adding this. But we already have a queue that we own, which has full transaction support, which is called MSMQ. So we're likely going to use that as the bridgehead into Service Bus, and are going to do fresh scaffolding around it. So MSMQ is by no means dead. Well, we look at Service Bus as giving MSMQ actually a new lease on life, because we're going to leverage Service Bus as leverage MSMQ as part of Service Bus. The backend store, by the way, of Service Bus has nothing to do with MSMQ. So the way transactions work here is very simple. You can go and send multiple messages, and you can go and complete it, or you can do operations like abandon, complete, set state, etc. Also within the scope of a transaction. Transaction must span, can only be towards a single queue, a single entity. If you start listing another entity, another client, the transaction scope will throw. Time to live is another thing you can do. The messages disappear once the TTL expires, and that will protect you against stale information, information that's no longer there. What's interesting with this is that you can go and combine this with a feature that we call dead lettering. So I'll talk about that in a moment, and I'm going to go back to the correlation story to complete that. So time to live, you set that very easily by setting time to live on the brokered message to a time span, and once the message passes that age, measured from the time when it has entered the broker, the message goes poof and goes away. Scheduling is kind of the brother of TTL. Scheduling, you can make a message appear at a certain point in time. So if you need to have a distributed clock in the system, you use scheduled messages. So you can say scheduled time, NQ time UTC to an absolute time value, and that's the point in time when the message is going to show up in the queue. So you can take a job that you need to execute tomorrow at 3, and you simply send yourself a message to that point in time, and then we're going to make it appear. What you can't do yet is cancel them. But that's typically okay, right? For many cases, it's fine if you don't have those cancelable. But you can, with this, you can effectively do a distributed clock. And distributed clock is very interesting because when you think about load balancing, now you can have many different receivers, right? 3, 4, 5 nodes, at least 2 for failover redundancy. And they don't have to keep their own clock. They don't have to run their own timer. You don't need to manage those timers, need to deal with offsets. You simply throw the job into a queue, and then one of the two is going to get it. So building a hot cluster that's doing jobs, you can, on a schedule, you can do using scheduled messages very easily. Then there's dead lettering. So you can go and take a message that you don't know what to do with, and you can dead letter it. There's 2 ways of dead lettering. One is explicit, where you call dead letter on the received message, and it goes into the dead letter queue. And there's an delivery count property on each message that tells you how often you've seen that message. So if you have the following situation, so you do peak lock, so you have this peak lock mode, and you have receive, process, crash. Receive, process, crash. Receive, process, crash. That's called poison. And if you find a message that's poison, that is poisonous for your system because it makes your system crash, because there's some invalid data in there, you need to get that out of the way, because it will always appear again. So what you do is you stash it away into the dead letter queue so that someone can take a look at it. We have a feature also on the description of a queue that allows you to dead letter messages when they expire. So they also go into the dead letter queue. The dead letter queue is just a normal queue otherwise. So you can create a client on the dead letter queue and just get the data back. So let me go and skip back to here, briefly. So you go from here, so you're in ASP.NET, and now you need to do things fast, right? So you want to get a transaction done within, let's say, 100 milliseconds. Queues are not necessarily slow, right? 100 milliseconds, 150 milliseconds is not a bad expectation for a round trip. Where our latency inside the system is between 20 and 50 milliseconds on a bad day to go from send to receive. So you can expect 150 to 200 milliseconds. So you do one of those. You need to do one of those reliable transactions. So what you do is you send the message in, and you sent it on the queue. You set automatic dead lettering on expiry, and you set the TTL for that message to 200 milliseconds. And then you have on this guy here, you have a receiver that sits there, and that's watching the dead letter queue. Well, now it can suddenly know whether the request actually went through, because if it didn't go through, it actually now sits in the dead letter queue. So therefore, you now have a feedback mechanism where you can combine TTL with dead lettering, with this automatic dead lettering, to see whether an urgent request actually has a chance of arriving, or whether it has effectively died on the way. We also have duplicate detection. If you have an operation and the operation is failing, but the operation has a deterministic outcome. So you get a message, you start to do some processing, now you crash for whatever reason. Right? It might be an error, might be the Windows Azure Fabric controller taking your worker role out in the backyard. So one of those things happens, right? Your role goes down. With that, we have now requires duplicate detection equals true, and duplicate detection history time window, we couldn't make that any longer. You set that time window. During that time window, we will remember all the message IDs we've seen. So if you can produce, as the outcome of a transaction, consistent message IDs based on the kind of operation that you just did, and you send us that message ID again, we're going to drop the second message. So that gives you kind of a way to avoid duplicate processing if you have to redo things. Because DTC is absent from the system, and that's true for all cloud systems and effectively for all highly scalable systems, you need to have effectively ways around this, and duplicate detection is one way around this. So you do the work again, and you produce the same message again, and because you have already produced that exact message, the exact same outcome, because the system is deterministic, hopefully, then we're going to effectively swallow the second message. And that's a very useful thing. Prefetch is a feature you can also set, and you can set that on the queue client as you create it before you receive. We set the prefetch count. That's exactly equivalent to the similar prefetch in the SQL client. The SQL client has a default prefetch of 100 rows. So when you go and get a result set, you get 100 rows in one batch. And then once you scroll down the cursor to 100 rows, it gets the next batch. Same thing here. We receive a batch of 50 messages for you. We load them into your client as fast as we can, and then you work off that local buffer, and then we get the next batch for you. That's a higher throughput option. The downside of that is lower reliability. Because if you do receive and delete, everything you've received in that buffer, if you don't fetch it, is going to be gone when your process goes away. If you use peak lock, then all the messages that are in that buffer are going to be the lock period is going to start when we fetch them. So you have to process that buffer, everything that's in that buffer, within the peak lock time window, within the expiration time window. So you get higher throughput, but your reliability management is going to be slightly more complicated, or you need to actually go and process it with high throughput. It's a high throughput option. So SignalR. So now we have all these different options, all these different patterns, ways to use topics, and people ask about scale. And they say, oh, I have these wonderful ideas, and now I need to run a website, and I want to have a subscription or a queue for each client, or for a mobile application, for in-app delivery. And that's where our quotas kick in. We allow 2,000 subscriptions on a single topic. It's not too bad, but when you think about true consumer scale, then you probably have several millions. Or people want to run games through a website, and then it all becomes a little heavy because you need to go and create those subscriptions, delete those subscriptions, etc., etc. Turns out SignalR is actually built for those purposes, and it's really nice for those purposes. It's a lightweight signaling library. To give you kind of the spirit of it, let me try to find it. Localhost SignalR demo. So I have that running on this machine. Let me just go and make a window here. And let's make another one. I should probably make that Chrome just for good measure, but I'm just going to let that be IE. And the simple one is mouse tracking. So I have two independent browser windows, and I can do things like this. Right? It's a little silly, but it's a lot of magic because that's all happening through a server-side event. The client does that and then sends a request, and the request gets broadcast to the other guy. So you can scale this up, this mouse thing, even though it's going to be very busy, to several thousand clients. It's not going to be a pretty picture, obviously, but you can. So that's beautiful. The way they do that is very simple. They have a simple programming model in JavaScript, so now that's a little slow, a little tiny. So let's go and zoom in on that. So the client has a JavaScript, and the server has .NET. There's actually a very similar thing for Node.js called Sockets.io. So all that I'm saying about that is also true for Socket.io in terms of the support that we're going to add to Service Bus for this. So you have this chat thing. That represents a hub that's being called the client. You have an operation send message. That's an operation that's automatically being projected into this is all getting code generated into the client. There's an operation add message, which is being created in the JavaScript on the client side, and which is dynamic function that's being called on the server side. And that's the extent of it. So the flow is, the client gets loaded, right? It gets the auto-generated JavaScript, and then it can go and send a message. So when the send button is clicked, then we're sending a message from the message entry field. That text, we're going to send that to the server. And then when the add message is being called from the server side through that notification channel, then we're going to append that to our messages box on the website. So you can easily imagine how that's going to look. And then that's the server-side code. And the server-side code is causing a broadcast to all the clients that are currently connected. Super simple programming model. You should actually check this out. It sits on GitHub, called SignalR. It's a wonderful library. The one catch with SignalR is it scales to exactly one node. It's a small catch. Which means, in effect, once that one node goes away, all the glory is gone. Right? So all the state is gone. And so how do we deal with this? How do we make it multi-machine capable? Or we're helping them a little bit. The SignalR infrastructure on the back is looking like this is what the architecture looks like. You have a message bus, and it's key value pairs, and there's a filtered receive, where it's actually asking for some keys. That's how they map internally this wonderful little programming model. And you have the browsers. And there's long polling support, WebSocket support, server-side events, and what they call forever frame. So 4 transports of varying sophistication. WebSockets being the most sophisticated and newest and most powerful, and then long polling being the somewhat most expensive. So the library can automatically figure out which browser supports what. And then you send messages into that message bus, and they pop out effectively to everybody who's a subscriber. So it's a super lightweight pops up infrastructure. What we're doing with service buses, we're adding a backplane to SignalR, and we've effectively contributed that into the project, where you can go and scale this out. You can make multiple nodes, as many nodes as you like, and interconnect them through topics. And you can add multiple topics to get higher throughput. So the notion here is that if you have more than 1,000 messages per second throughput through a topic, you just add another topic. And the library is actually automatically going to go and provision those topics for you. It's going to manage them for you. And then it's also dealing with failover from, you have a client, the client runs on one node and then gets load balanced over to another node. So it makes sure that all the messages are in the right format. So if you want to build something like a game, you can now scale it out to hundreds of thousands of clients that are running concurrently, and the messages that are flowing between them are running through the service bus backplane so that they're available on all those machines. A nice side effect of that is, because it's now a topic, you can now send also from the bottom. So if you wanted to show breaking news or stock ticks or whatever you want to do, you have all these front-end clients that are connecting through SignalR using these lightweight subscriptions, and you're pumping data into the topic out of your normal application, and that then gets distributed into all those clients. So that's another thing you can do. That's actually why we do this, because we need a lightweight, web-integrated subscription mechanism, and so we're using SignalR for that purpose. Summary. Landed on time. There's still more. That's not all. Get the SDK and associated samples. They're showing a lot of those capabilities in detail. The more of these, most of these samples actually work through the REST API. You can actually do them from most platforms. What we try to do as part of the Windows Azure SDK, so if you go to windowsazure.com, is to make all those capabilities available for PHP and for all kinds of other platforms, for Java, so that it's not only usable from .NET, also the AMQP capabilities that we're going to have. The AMQP protocol is also going to support most of those features. So you're going to get this for hosted in the cloud, available for integration across applications for integration inside of applications, for building backplanes for your systems, or to build the messaging fabric for your systems, not only on .NET, but across the whole platform. And again, as a reminder, if you are in Stockholm tomorrow, you may want to go to this site, swag10-estw-eventbrite.com. I'm going to put this up again. And come join us. There's still 20 tickets free. Why is that the case? There's still 20 tickets. You can get the tickets if you happen to be in Stockholm tomorrow night and you want to go 5:30 at the offices of No IT. We're going to continue with a little bit of a jam and go through additional scenarios. Thank you for coming to my session. Thank you for coming to TechDays. Thank you very much.